Yeah, another draft physics video production and such. Should be anyway. So we'll do a little Professor Lewin for making a point. We'll read a comment. It's only one. And we'll do something else after that. Yeah, that should cover it. Lights, please. Okay. Good enough. So here, Professor Lewin is going to explain how photons are created, and so it's sort of funny, just because the explanation is pretty much photons make photons, which doesn't, from their point of view, that's not saying much. Pause now. Alright, back and such. So let's play the video and such.
And the answer that I have to give you is a little bit embarrassing, and that is we accelerate charges by exposing them to electromagnetic radiation.
Alright, so this whole accelerating a charge thing doesn't really create any difference. The point is that electrons and protons are already charged in the sense that they're in a relationship to each other based on the fact that they're emitting something. Obviously, they're doing something to the universe. And that's why they behave differently towards each other. The electron to the electron, the proton to the proton, and the proton and the electron having the opposite reaction of attraction. So clearly they're already doing something. And they don't do something different when you're moving them. You're just moving, that what they're doing in the universe. And as I've pointed out, if you move them away from each other, then you're going to change the dipole, The magnetic part is going to come in balance or out of balance depending on distance. So as I've attempted to point out, how much of this you can see is sort of dependent, on how close this is to you. See, the closer it is, the less of this you see. And the closer it is to this, the more of this you see. That kind of thing. That's all you need in terms of a change. So all you have to do is change the position of the electron. You don't have to move it somewhere. You change positions and then you create a change in the field that both of them are creating from a distance. What you're going to see them, it'll seem like they're different. Fundamentally, you haven't changed the electron and the proton, you're just changing their relative positions. So when they say a moving charge, it's really not right. You don't have to, it doesn't have to be in the active process of moving. It just has to be changing the field because the positions change. And then you'll change what its magnetic profile is, if you want to call it that. Its charge profile changes as you change its position. And then this gets into the fact that you have to keep changing that field if you want to convey pressure in a wire. So if I create a magnet and I move a bunch of iron filings, they don't move any further, right? I move them a certain amount and they stay there, and I need to let them move back somewhere else. So let's say they were sort of on little springs and I push them. Well, if I don't change anything, they're just going to stay there. They're not going to do anything. So that same thing happens in a wire. It gets sort of clogged. So you need an alternating current in the sense you need to let them relax so you can push them again. You can't push them if you don't let them relax. If you don't let them pass to be pushed again, you can't keep pushing them. So you got to allow them to keep moving. So it's sort of, you could probably find a parallel in water. If you had a wedge that you were pushing into the water, you push the wedge in, and if you don't let the water fill again, you can't get any pressure in the water. You can't move it unless you relax the pressure so you can push again.
And then you say, well, isn't this catch-22?
I don't know if it's catch-22. It would be some other kind of paradoxical thing, a circular reasoning, some other kind of thing, but it's a little, okay, we'll go with that.
Because you have to accelerate them to create electromagnetic radiation. How do you accelerate them? Well, you have to expose them to electromagnetic radiation.
Right. So the point is the behavior of the fundamental, the elemental elements seems to be a consistent one. So that's sort of what I would argue. It's not strictly a photon necessarily that's moving the charges. Clearly, it doesn't have to have frequencies. It doesn't have to have a lot of the things that we associate with electromagnetic radiation, but clearly, in a sense, okay, it has to create the pressure that's necessary. It creates the pressure. The frequency is imposed by the consequence of the depressurizing.
For whatever that's worth, of course, there is electromagnetic radiation that comes out of all kinds of sources.
Right, and it comes in forms that we don't often see, most of them, and so we're not really appreciating the fact that there's a bunch of radio waves bouncing around in here in this room, and I'm not aware of the different things that are reflecting it more and the things that are absorbing it. So the things that are light and dark in the radio spectrum is completely different than the things that are light and dark in the spectrums I see in and all of that. And yes, we lack appreciation for the density of the amount of this force crap that's floating around that we don't see. And I would argue the biggest one is gravity. Same force, same mechanism. It's just not at a frequency we can detect.
And so I will show you now that if we take an electromagnetic wave, we'll take a linearly polarized traveling wave, and we will expose an electron to that radiation, and then we will...
So let's understand, so you don't need to have a polarized anything, you don't have to have any of that stuff. You just need the current in the wire, so you just need pressure. You need something to change the position of the electron relative to the proton to create a change in the external field that you'll perceive around those objects.
See what the electron will do with that incoming traveling wave. A plane wave.
So again, it's nothing to do with waves. You don't need a wave.
So here is that electron. It has charge Q, which is now negative. It has mass m. And from the left comes linearly polarized radiation. That's what I have chosen. E0 cosine omega.
So let's just understand the polarization can be argued to be just the fact that it has it's not coming in exactly a laser beam. It's a little bit out of alignment, and the amount of out of alignment is time sensitive in terms of how it was created. So the faster the little bits are coming, the less time there was for the position to get screwed up. So in all likelihood, there's going to always be a proportional relationship between the frequency and how much out of alignment the radiation is. And the out of alignment can be in both dimensions or just in one dimension, depending on how the photon was created and what material.
So it just comes in, it's a plane wave, infinite in size, it comes in like that, and this electron begins to shake. And the
Infinite in size, I don't know what you mean by that, but whatever.
force that the electron will experience, F, is Q times E0 cosine omega t, right?
Right, but these quantities don't have any value, like the E0 doesn't mean anything. That's just, you're basically saying the force is equal to the energy, and you're just turning the Q into a constant because it's an electron. So yes, they're all the same. So you're basically saying, yes, force is equal to energy. Yeah, okay, sure. Or the electric field, in this case. Let's understand the magnetic field, in the math, is divided by C in terms of its intensity relative to the electric field. So it's divided by the speed of light, smaller. So they always draw them like they're equal. They're nowhere even close. But the effect, again, is the point. The point is the electric and the magnetic are not, they're all the same thing. It's just force. And that's it. There's nothing else involved. So I don't know how to change the language to make conversation more constructive. The fact is, photons create electric and magnetic phenomenon, but they're not made of it. They are it.
That is the definition of electric field as it is connected to force. Now when the electron, I do this for bound electrons. So these electrons are bound in an atom or in a molecule.
So this is exactly what I've been talking about. The fact that they're already in tension, and what you're basically doing is aggravating that tension. So you're basically separating protons from electrons. You're moving electrons, which is making more distance from the proton. There's a natural position for the electron to be in. It was already in equalized pressure. The attraction to the proton was equaling the repulsion by the electrons. The scenario was that it was in some sort of balance. You're kicking it out of that balance. So there's every probability that if you don't kick it out hard enough, it's going to go back to its original position when you're done irritating it.
Bound electrons. So when you try to move them away from equilibrium, they don't like that. They experience a restoring force because...
Yeah, so they call it a restoring force. There's no restoring force in the sense that they go back to the fact that they were in a equalized position. You put them in an unequalized position, an imbalanced place, a place in space that isn't balanced. The fields aren't balanced for them. So they're obviously, going to be migrating back to the balanced state.
Of the Coulomb interaction in the atom, and they want to go back. So there is...
Coulomb interaction, he's just saying the charge interaction, the fact that you've taken them from a position where they were stable, you put them in an unstable position, and if you don't do that, if you don't escape gravity, you fall back into the gravity. It's that simple. So if you don't have enough energy or fuel to escape, you will be dragged back.
The restoring force that acts to some degree like a spring, and so there is also...
So it's exactly, basically, what my redefinition of the terms. It's the same story. They're just telling it wrong.
Then a resonance frequency associated with...
So exactly what I have been saying, that the whole point is that the tension is defining, whether you can kick an electron. The tension is defining what frequency is required to do that, because it's going to decide how much the electron moves back. So you're just really saying what's the tension required to to have a speed that will tip something over. It's a tipping point argument.
With that restoring force. And so that resonance frequency I will simply call omega 0 squared, which is then k over m.
So this is where they sort of just make up definitions, because there's nothing coherent about that. All right, this idea of, well, we're going to square the permeability of space, and then we're going to call that a constant, based on the material divided by an arbitrary m.
Is then the equivalent of the spring constant, which now acts in the atom.
So they're using these terms, but I'm just saying I don't think there's any precision in this definition in terms of defining the exact tension that the atom is in. But that's not a big deal. So I don't know how much, there's probably no point in going further just because it's all just going to be mathematical crap. But the point is made, is that the photon is really as a byproduct of the electron moving back to its position. And how fast it does that is dependent on how much pressure is surrounding it. And so depending on what the voltage is and what the atoms are made out of, that's going to sort of dictate what kind of photon's going to fly back out. And of course what kind of energy went in will dictate to some extent what energy goes back out. How fast the electron got out of position will in some sense dictate how fast the electron gets back to its location. Kind of. Alright, so what else do I want to talk about? Alright, so yeah, I'll read a comment and then I'll go back to something else and then I'll go back to something else. I can do that. I'm semi-professional. Alright, so Alan Fairbacher. Anyway, while you're correct that Ken Wheeler's videos on the gyroscope and the magnetic field of the really big magnet are complete nonsense, your explanations are also incorrect. Fuck you. So he's not going to quote anything I said in the video. The only thing I'm arguing about, right? I mean, I could have just said, it's eddy currents, like the rest of you morons. But that doesn't say anything. You're not explaining where the process or what's causing an eddy current or where it comes from or how it moves or any of that. And that's my whole point. So I wasn't incorrect. I could have used your terminology and I could have just said it's an eddy current. But the truth is it's more complicated than that. You're exposing a paramagnetic material to a force and you're not explaining why does it create a breaking magnetism. That is, why is it creating the same magnetism in return instead of complementary? So where a piece of iron goes complementary, that is, it creates an inverted magnetic field that is attractive, the paramagnetic material produces a well, I would even say the iron does the same thing. It's just that the alignment of the magnetic bits, the atoms inside the iron, overwhelm the pressure change caused by the paramagnetic effect. So it's just a subtle difference, but it's an important difference. So what's really happening is that whatever you're exposing the metal to, it's being pressurized. So if you're exposing it to less pressure, that is proton pressure, okay, that creates the same effect in the sense that it expands or contracts atoms. So it either makes them closer or further out. So if you expose them to electron energy, they get fatter. You expose them to proton energy, they get smaller. All right, so that's the theory. That's the point. And so that is what changes their magnetic field. So if you throw electron pressure at them, you end up getting electron back in the sense that you push the electrons out, which makes them closer and relative to the proton, which means that you'll see the pole as being the same pole that you produced as energy. Wherein when a piece of iron is reacting, that pressure effect is happening, but the more important effect that's happening is that the atoms are already dipoles and they're turning, and they're all turning in the same alignment, which makes them a collective magnet. And so that becomes more significant as an effect, a lot more significant. But anyway, this idea of a current, there's no eddy current. Okay? There's the change in the size, the pressure of the atoms, and that in a conductor moves. The pressure is spread, all right? But instead of spreading front to back, it's spreading across the surface, and that's the difference. All right, but I wasn't incorrect. And again, if you're going to say I'm incorrect, then quote what I said that you say is incorrect. Because I said, basically, I even said in the video, I'm quite sure I said, the eddy current explanation is okay, but it's not complete. This stuff is physics 101. Whatever. Yeah, you think physicists have it nailed. They understand exactly how and why eddy currents are created. What they call an eddy current. The phenomenon of the complementary magnetism. You say they have a great explanation for all of that. I say they don't have anything close. Okay, and a correct explanation, so again, more nonsense. They don't explain how it happens at all. They just explain the effect. Again, they don't explain the causes of the effect, the mechanisms of the effect. They don't tell you, they don't talk about what happens to atoms at all. They just say eddy current. Can be found by carefully thinking about magnetic braking. Again, those are just words you put together. And magnetic braking just means that instead of instead of creating an attractive magnetism, you're creating a repulsive magnetism. Wikipedia has a good article that shows drawings to help with the thinking process. Screw you. All that is going on here, there's nothing that simple, is that when the gyroscope is centered on the magnet, the wheel is spinning in a uniform magnetic field. No, it's spinning essentially on top of a monopole. So it's not that it's just uniform, but that's true, it's sort of uniform. But the more important fact is that it's one field. It's not different. It's not a mixed field. Essentially. So it doesn't have any of the consequences of being affected by a dipole. Hence, no net magnetic or electric forces. So again, this idea that there's no forces. There's plenty of forces. The key word you said there was uniform. They're in balance, the forces. All right, there's just as much of it on one side as there is on the other side, blah, blah, blah. And obviously, when you don't have that condition, then something else can happen. Yeah, things change when you change the environment. And what changes is the field goes from being uniform to not uniform. But when the wheel is pulled to one side, it is spinning in a non-uniform magnetic field. Well, the point is it's now exposed to the south end of the magnet. See, when it's sitting on top of the north end, okay, there's very little red pressure that could possibly be getting to it, right? It's just a minimum amount. Depends on the strength of the magnet, how well it's made, lots of things can decide that, but the idea is that, yes, there's not too much exposure to any kind of red, okay? And then once you get to the edge of the magnet, though, then the red stuff is now free, so to speak, at these really sharp angles to mix into the field. And so now you're getting a dipole field. All right. Non-uniform magnetic field, which produces eddy currents in the wheel. So you don't explain how it does any of that. How exactly does it produce an eddy current? Right. Exactly as in a magnetic brake. So again, you're just basically saying exactly like in eddy currents. It produces eddy currents just like an eddy current. None of that's explained by you people. So you just say these words like, oh yeah, well, it's a magnetic brake. Created by magnetic braking. It's the magnetic brake effect. You're not explaining any of it. These eddy currents oppose the non-uniform field. They're not opposing it on purpose. They're reflecting it. So that's all they're doing. They're just reflecting the field that's hitting them. Okay, that's it. Of the big magnet, thus slowing down the wheel. So, wrong, but whatever. Again, it's just, I don't know what to say. They're obviously, I'm just saying they're creating a conflict. All right, so nothing's symmetrical anymore. So the magnetic fields are essentially fighting each other now when it's spinning. Instead of being consistent with each other, they're fighting each other. All right, that's slowing down the wheel. Simple? No? Question mark. No, there's nothing simple. You say magnetic braking. Oh yeah, everybody knows what that is. No. And again, they don't have any physics explanation. They don't have any causal chain of reasoning to explain the process that creates that braking. And why is it different than with iron filings or with some other kind of material? They don't make those distinctions or give any of those explanations. So, screw you and this arrogant tripe, frankly. And again, screw you for implying that I suggested something other than the fact that it's a mixed, ununiform field. When I said that's exactly my argument. It's exposed to the red end of the magnet. It's exactly my argument. So how exactly was I talking about non-uniform field, idiot? Yeah, so I'm going to delete it because it's just obnoxious. You didn't demonstrate I was wrong about anything I said. So quote where I said something wrong. Oy. Okay. Alright. So, alright, something else I was thinking about. So I guess we can go to that. And then we'll do some other physics video. Maybe I'll do the video first. Well, let me just do the argument. Alright, so I was thinking about reflections, and what first led to it was a thinking about how they define the size, not just the mass, which I would say is, again, based on assumptions. They have to make certain assumptions about what they're doing to tell how big something is. So the classic experiment to decide, I guess I'll use the red because we're talking about protons. So they have a classic experiment where they want to find out how big a proton is. And so what they essentially do is shoot protons, okay, at atoms. So this is an atom. And they want to find out how big the nucleus is or some other kind of part of this atom. And so they shoot these essentially protons, or nuclei, at nuclei. That's sort of the idea. And they count what they get back. Okay, what bounces back, they're assuming that's when it hit a nucleus. And there's a lot of assumption in there in terms of, well, first you have to assume a shape of some kind, because you don't know how well this reflects back. I mean, if this was a diamond shape, right, or off square, these reflections are going to be sharper, and that means you're going to be less likely to ever get this one back. You're not going to see it come back because it's going into the material. Where if, and the only place you'll get a direct reflection is one place, depending on shape. But let's just assume a round shape. The idea is if you hit the force directly on, perfect on its center of mass, you can have some expectation that you'll get a pretty close rebound. But if you're a little bit off, you could expect that you're going to get some kind of reaction where you get this, and this proton goes this, the nucleus gets pushed that way, and you're not going to get anything back to tell you that you actually did hit it. You're not going to know you hit it. Okay, it's just not going to happen. So this is a pretty crude way to tell how big a proton is, or more importantly, how big. I'm talking about volume versus density, I guess. Because we're really saying that this stuff has to hit stuff is the whole idea, right? I mean, a photon has to hit an electron. And if we have these things sized at these bizarre sizes where they're saying that 99% of this place is just empty space inside of this atom, that doesn't really make a lot of sense, because you're saying it'd be pretty hard to hit one of these little things then. This is a pretty tiny amount of space in the space, and you're not very likely to hit that. So this, sort of doesn't make any sense to me. And certainly the electrons, being as distant they are and as small as they are, it really gets kind of, what's the likelihood of actually hitting one of these electrons with a proton? So I don't know if this diagram fits at all. I mean, I think, I just don't know if there's any other facts they have, any other evidence they have to decide how big these pieces are. Because I guess I would sort of argue that I think atoms are full of electrons and protons in a higher density, that there's not all that empty space in there, that this thing is, these electrons have to be kind of big. Okay, they can't be little things. Now their mass might be small, like the sun. Sun is really big, but its mass is only 8 times well, not 8 times, but it only has 8 times the surface gravity of Earth. So its mass is small compared to its volume. Its volume is huge, but its mass isn't all that tremendous, relative to the Earth. So it's only, I don't know what the geometry says. I mean, we could say 23 times more massive than the Earth, but it is, like whatever, a million times bigger, more voluminous size. So you're just saying that the same mass could be in this volume or the mass could be in that volume. And I'm just sort of arguing that I don't care what the mass numbers are so much as I'm just saying that these proportions of size, I would argue, have to be something a little more, has to be something more like this than their model, which is, minuscule dots in space, that you could, that are taking up no space. So I don't think atoms are as formed exactly as they state. So anyway, thinking about that got me thinking about, I don't really talk about the proton too much, and I keep saying how, it's electrons are everything, but the truth is that protons do interact, and they are a real thing that energy can really hit. So I was thinking about the idea of light reflecting, and the fact that, okay, at this angle you hit something, a surface. This is a surface, let's say, with atoms, electrons and protons. You have a certain percentage, an index of reflection that you can expect at the perfect straight-in angle. So you could argue that for glass, it's whatever it is, 4%. There's a 4% chance that the light will reflect back when you come in at a 90-degree angle. And then as you change this angle, okay, the idea is that you're more likely to get a reflection. This goes up to 20% or something. And then if you get to certain angles, it's like you've guaranteed it. You've got a 100% chance that all the light will reflect. So in thinking about that, I was thinking about protons and the fact that they're just doing this right turn thing, basically. The energy comes in and the energy goes out when it's photons, when it's in the form of this black energy, which the photons are made out of. And so black energy, the negative energy, the two kinds of energy, red and black, two kinds of charges, protons and electrons. So anyway, and photons are made out of this stuff. The pressure between the black pressure that comes off electrons is what's at a frequency to create a photon. But anyway, so the point is if it did hit if you sent a photon into a proton, the odds are it's going to do this 90-degree turn, is what I'm saying, is the theory. And if you think about that, then it sort of makes sense, especially when you think of this proton being a little bit deeper in the atom, because you didn't hit the first atom, you missed that one, the second atom, so you might not only hit, you might hit a proton back here somewhere. So the point would be is that the more this angle, the sharper you can make this angle coming back, theoretically you can just understand that you have a higher probability that this is going to escape. So the more the angles like this, or the more the angles like this, the less likely. So if the light comes in straight and it goes this way, well, it has a 50-50 chance. It could, it could hit another proton, go that way, or it could go that way, or it could go in, or it could go out of the board. So there's only a 1 in 4 chance of the 4 choices, right? In, out, left, right. Right? There's only one choice that gets you where you want, 1/4. So only 1/4 in the first interaction will even get you back out. So it'll create the U-turn. That's what we're looking for, right? It's a U-turn. We're looking for it to go in, do something, and come back out again. Physics can't do a pure reflection, let's just argue. It doesn't do that. Homie, don't do that. Because the proton is going to move the electron. So if you hit an electron, yeah, it's sort of a reflection, and it goes right back to the source, but that's not the part we're trying to figure out. We're trying to figure out what the reflected part, and that's not the reflected part, because that goes back to the source. You never see it. You can't even detect it. There's no way to, I'm not saying there's no way to do it. It's tricky. You have to shoot light and then put a detector back to see the reflection. But anyway, the point is the electron gets momentum, and it's the electron's momentum that eventually creates the new photon when this movement ends up being exchanged for the movement back to normal. But anyway, so I'm just pointing out that obviously when the light comes straight in, the choices are not going to be necessarily going to get you the light back at a very high percentage. Where the more I change that angle, the more I get this angle heading for the surface, the more likely it is that it makes it out without being interfered with. And of course, at certain angles, if I hit the proton, I got like a guarantee I'm going to get back out. You know, because there's not going to be any more protons in my way. So the sharper this angle is, you know, the more guarantee you have. So I think this works as an explanation. So I just haven't thought through every permutation. But reflected light, this might explain why it has certain polarization, like glare. It might explain some phenomenon that exists because there, you know, reflected light might actually be light that hits the protons rather than light that hits electrons. It might come down to something that simple. Yeah, and that's why the frequency stays the same too. It's because it just goes into the proton and all comes back out. It's only it's the simplest event that can take place physically, you know, in terms of there's just nothing complicated about going into a proton and popping back out again. There's nothing complicated about it. So proton doesn't absorb any momentum in the process of diverting the black energy, just like the electron doesn't absorb any momentum in diverting the red energy. All right. So just something I thought of that seems to fit again. You know. Just, you know, just another example of the model working. Okay. To explain what we see. All right. Anyway. All right. So enough of that. So I guess we will move on, because there isn't much else. So I'll go back to one of these science please kind of things, and we'll do this second one on quantum mechanics. I know I have something funny in it. Stupid. I mean, dumb. You know, there's bound to be something. Now, I have to hit the play button.
In the last video, we learned that there was quite a large difference between the measured spectrum of the black body and the spectrum predicted by classical physics. They were consistent in the...
So again, there's no prediction by classical physics unless you say classical physics had some mechanisms and all that stuff. And this is all part of the stuff where nobody made any classical predictions. So he's claiming they made classical predictions when they didn't make any such predictions, because Newton didn't even know about all this atomic structure even existing. Didn't even, you know, so it's really cheating, you know, to say they made predictions when they didn't make those predictions, because they didn't know what the phenomenon was. I'm just saying we're getting to the point where this is the whole Einstein argument that you need a certain frequency of light to be able to perturbate the electron or agitate it in the manner that it needs to be agitated. And as I just pointed out, or as Professor Lewin just pointed out, there's a resonant frequency, there's a tension that these particles are in, and that tension is going to decide what energy is needed in what form to knock it out. Just like how heavy the post is I'm going to shoot with bullets is going to decide what its tipping point is, you know, and what rate I have to hit the bullets into it. You know, so they didn't have an opportunity to predict something. So again, to say that there's some sort of classical physics that they're debunking, they're not debunking any classical physics. They're not debunking any argument made by anybody. They're just straw-manning classical. They're straw-manning the word classical again, claiming it said things it never said. Almost like where they say Newton said gravity is instantaneous, when Newton didn't say anything on that. He didn't know. He didn't say. He didn't make a declaration. I have evidence that gravity moves the speed of light, or gravity is instantaneous. He made no assertion.
frequency limit, following the Rayleigh-Jeans frequency squared law, but diverged around the ultraviolet region, creating a problem known as the ultraviolet catastrophe. Such a large discrepancy between theory and measurement is clearly a huge problem. I mean, if it were just a slight deviation, it could be that the theory was out by some factor, or there was a significant source of error in the experiment that went unaccounted for. But such a total difference usually points to a bigger problem with the theory.
Right. So again, they're not debunking a classical theory. They're debunking another form of a quantum theory. So it's just, just nonsense.
With the ultraviolet catastrophe, this problem was partly due to the assumption that the equipartition of energy held over the entire frequency range. For low frequencies,
yes, it's based on some assumption that all light is equal. Okay, and it's all as easily made as any other form. So it's just kind of ignoring the obvious, where you could argue it's a lot harder to create higher frequencies. You need more and more special circumstances where almost anything can create this frequency. Small things, big things, anything can create some frequencies. Only small things can create really fast frequencies. So there's certain, just even, simple intuitive explanations for why you can't make a big giant bell that makes a really high frequency sound, that kind of thing. There's intuitive reasons to understand, no, there's a difference, and only certain mechanisms can make very high frequencies, and only other mechanisms can make very low frequencies, and there's not going to be any rule, or law that says they're all the same. That would be stupid. That they all happen in nature at the same rate. So the simple argument is that high pressure zones are rarer. The highest pressure that would create an X-ray, for example, are more rare than the locations that have moderate pressure. And you could just say, duh, right? Just like in the Earth, there's pockets of pressure probably that are extremely high, but there's an average pressure that's much more moderate and much more available.
the classical prediction seems to be approximately true, but clearly there's some kind of frequency dependence that's not being captured by this classical picture. It seems that maybe our expression needs to be corrected with some function of frequency. Not only did the classical prediction not match the...
So again, just more gibberish that somehow, like I said, people who didn't know didn't have information to even posit an opinion, they're putting words in their mouth to say they couldn't answer a question, when obviously they can't answer a question about something they don't even know exists. I mean, people who didn't know microbes existed couldn't speculate on inventing penicillin.
Data, but it predicted some pretty weird phenomena too. We could try to calculate the total energy by adding up all of the contributions from each frequency, which would be an integral since the spectrum is continuous. Clearly when we do this, we get something that diverges to infinity. This would imply that these kind of systems in reality can never come to thermal equilibrium, since no object can actually have an infinite amount of energy.
Right, so again, it's not about how much energy, it's about having a mechanism that's capable of vibrating at this incredibly higher speed. So you can just understand, if I have a big clock pendulum, it's going to be really hard to make the physical matter, vibrate that much, move that much mass to make it vibrate fast enough. It's too much mass to move too quickly, and there's no process for doing that, because we know that acceleration takes time. It's not a perfectly efficient process. It's even going back to the gravity argument. Gravity, because it's hitting your littlest bits, is more efficient, let's say, at applying the force than, say, accelerating you in a rocket, which is going to cause you to crush, and lots of stuff is going to have to be. It's going to take time for the acceleration to move through all of your atoms. So it's almost as simple as that argument. Some things, a piece of steel will survive acceleration where a bowl of Jell-O won't. Well, bowl of Jell-O is probably a bad example because it starts off already kind of gravitationally neutral.
However, this is contrary to what's actually observed. Many systems do in fact equilibrate whilst having a finite amount of energy. So what was the resolution? Surely physics isn't broken, is it? Well, Max Planck was able to resolve this problem. However, he didn't really develop his solution in response to the problem. Planck's motives were rather more complicated and not all that important for our purposes.
Yeah, this guy's voice is a little bit irritating.
but essentially he didn't really believe the equipartition of energy to be a fundamental law of nature. Before we get to Planck's solution, let's spend some time developing the statistical mechanics that we need, namely the Boltzmann distribution. In a thermodynamic system, particles will exist with a range of different energies. They might fluctuate a little bit as the particles bump into each other or into the size of the container, but the average energy should remain pretty much constant if we don't change the temperature.
So again, yes, you say the same temperature has the same amount of motion in it, and it can be in all kinds of different forms, in the sense that you can have some parts of the motion are slow and some parts of it are really fast, and you can have any kind of mix of fast and slow to get to a mean amount of movement. Well, duh.
When we measure a thermodynamic system, we could observe it in one of many different states, each state being defined by how many particles have a certain energy. Say if we have a system of 10 particles, we could have 5 particles with an energy of 1 unit, 3 with an energy of 2 units, none with an energy of 3 units, and 2 with an energy of 4 units.
Right, and the whole point of this argument is that the rule is that you're going to have less and less of the ones at very high pressure, because there's less opportunity in the universe. So the point is that in the structure of the atom, some electrons are under higher tension than other electrons. And that's really all it's saying. There's some positions that are more tense than other positions, and the ones of high pressure are less accessible, we could argue, than the ones of low pressure, that the low pressure is on the outside and the high pressure is on the inside. So you can almost make the argument about the thermodynamics of the Earth. The highest temperatures aren't on the outside, they're on the inside. And they can't get to the outside. They just can't get there very easily. And it's only under a special circumstance where you could poke the Earth in a certain way where you can actually get to the real blood, the high temperature, and let that out. So it's the rare event where you access the high pressure radiation.
Or we could have some completely different arrangement with the same total energy. Each specific arrangement is what we call a microstate. When we measure a system, we really observe macroscopic details of the system, variables like temperature, density, and volume. They aren't concerned with the fine details, like how many particles have what energy, but more the overall picture, like the average energy of all of the particles.
Right, but that would be stupid if you're thinking about the Earth and you're trying to figure out how it's insulated and how it what's the probability of a particle getting to the surface. Well, it's clearly going to matter whether it's on the very center of the Earth or whether it's on the surface of the Earth. There's going to be a huge difference in its probability of being free. Huge difference. Like the ones in the center have no possibility of ever getting out because they have to have a million, perfect circumstances to ever migrate out. And there's just no probability. There's a probability they'll get a couple of feet higher, but there's no probability getting higher than that 2 feet or 3 feet, and so they're just inevitably going to be stuck because they're never getting out.
So say we have a system of n identical particles at equilibrium. N is generally going to be a really large number, something like 10 to the 23 or more. Although the collection of particles will have some average energy, there could be a whole range of specific energies epsilon I. We might then ask the question, if we choose a particle at random, what's the probability that it has energy epsilon I?
Yes, well, you can't do this. This is just, again, so this is just more kind of silly, right? I mean, choosing something at random with choosing something inside the atom or choosing something outside the atom, choosing something on the surface of the atom, choosing something in the nucleus of the atom. It's just, there'd be no sense in it if you're not going to understand that there's a proportion of the universe is in one condition, a proportion of the universe is in another condition, and there's just statistical facts. There's more electrons under this much pressure than there is electrons under this much pressure in the whole universe. And it's just a fact. There's a different amount of them under those different circumstances.
Well, as it turns out, it's well defined. The probability distribution is known as the Boltzmann distribution. The probability that a particle has energy epsilon I is 1 over z times e to the minus epsilon I over kt, where k is Boltzmann's constant and t is the temperature. Z...
Right, that's very helpful, right? But yes, clearly this temperature thing is going to be the key. All right, in any temperature, there's a certain number of atoms, and so again, this is just always going to come back to some constant in terms of a fundamental fact, an elemental fact that you could say about all atoms. But obviously these are all going to be specific to some material constant, which you're heating.
Heat is a normalization factor called the partition function that ensures the total probability is 1. It comes up frequently in thermodynamics and statistical mechanics. The factor of 1 over kT is also sometimes just written as beta. This is often called the thermodynamic temperature. I want to talk about the partition function for a second, as it can be quite confusing. Firstly, the partition function...
And it likely does nothing. You know, so many of these equations are kind of funny just because the amount that this certain thing is changing anything is minuscule. And so they'll have a whole hunk of an equation that, you know, will only range from 0.003 to 0.005 or something, you know, some tiny amount of difference in a number that you got like 23, you know, or 24, 25, you know, and you know, it's just not that relevant.
Is defined as a sum over the single particle states of the system, each state being defined by its energy epsilon I. It's perfectly possible that some states may have the same energy. For example, you could have the energy of the first state equal to the energy of the second, but you would still have to include all the terms in the summation. Sometimes to avoid this, we include what's called a degeneracy factor, which accounts for the states with the same energy.
So they're pretty much talking, when you start talking about states and energy, you know, it's really talking about orbits, you know, and I'm not saying that things aren't at a distance from protons, but I don't think they're orbiting. And the energy is decided by their relationship to the other electrons, not their relationship, not their momentum. So it's not the speed of the electron that has anything to do with its energy. The energy of the electron is completely dependent on how much pressure it's under based on how many other electrons it's associated with. Period.
This way we just have to sum over the energies that exist in the system, and not necessarily the individual states. The difference is really subtle, and I will discuss it further, but it's not going to be too important for what follows.
I guess, yes, exactly. So why didn't you just say that? It's really subtle, it's useless, so why did you think it was important? You know, because it's not. So, you know, I just think of a way to illustrate a difference. Okay, so you can have electrons, you know, an electron that's just in the universe, or you can have an electron that's associated with a bunch of other electrons, and it just happens that he's the electron in the monkey in the middle. Okay, and these electrons are being, you know, you could argue being pressurized by other electrons. Okay, and so obviously this electron could be, all right, under a lot of pressure because he just doesn't have any choices of freedom of movement. There's no place to go without ending up closer to an electron, and he just doesn't want to get closer to another electron. Where obviously this one out here can go somewhere where the other next electron is way far away, so he can move somewhere better. And let's say the proton energy is somewhere associated with this. So you could argue that the electrons of, say, a neutron, you know, the proton-a-neutron pair, a proton-electron pair that makes a neutron, would be an electron that's sort of in this monkey in the middle position where he doesn't have a lot of options to go somewhere. Okay, and it's not until you free him from this atomic structure that all of a sudden he has a chance to decay or escape. And he'll do that. Over a period of time of opportunity. So when opportunity arrives, he will take advantage of the opportunity and decide to no longer be a neutron.
I'll leave it for a series on statistical mechanics. One last thing to mention about the partition function is its meaning, what it's actually telling you other than just being a normalization factor. The partition function is essentially a measure of the number of accessible microstates of the system. This is by no means intuitive, and it takes a bit of manipulation to be able to see that. The partition function is more than just a curiosity, however. It's really the most important quantity in all of statistical mechanics, as any macroscopic thermodynamic variable, such as temperature, pressure, or internal...
I would argue that I suppose it's somehow important. A partition factor is just, again, a recognition that the magma is different than the blah, blah, blah is different than the blah. You know, going out from the hottest to the coldest those regions are different, and they're the ones being partitioned, and that's what the factor is for. But I guess I don't, obviously I don't know what any of this gibberish really means.
Energy can be calculated from the partition function. Anything you want to know can be calculated from the partition function. So it really just packages up all of the information about the system and provides a natural bridge between thermodynamics and statistical mechanics. Okay.
Yes, I don't think there's anything natural about it. It's obviously not a natural language. You haven't put any kind of real identifiers in here. I have to figure out what this L is, what this N is, what this B is. I mean, B is traditionally B field, blah, blah, blah. None of that's, just nothing natural about any of this crap.
Rant over. The derivation of the Boltzmann distribution is quite lengthy and not really vital to what we're going to be doing here. But I wanted to cover it anyway, so I'm leaving it for an appendix video which will be out at some point after this one.
Very exciting.
You can check that out if you want to learn a bit more about statistical mechanics. But for now, I hope you won't have too much trouble in accepting that this probability distribution is true. So, where were we? Oh yeah, right.
Right, we were supposed to just accept that they figured out exactly all the states that atoms are in, and they have it nailed. No, I don't necessarily think you've done that.
We were trying to solve the ultraviolet catastrophe. The problem with the ultraviolet catastrophe...
See, there's no ultraviolet catastrophe because the perfect rational explanation is that there's a lot fewer electrons in the universe that are in a position to create ultraviolet, that have enough tension, that are going to be rushing back to a proton fast enough to create ultraviolet radiation. So it happens less often. It's not the same event as what's happening to the electrons on the outside. So there's more outside electrons than there are inside electrons, and it almost comes down to something that simple. So the whole catastrophe only exists if you think all the electrons are the same. But if you understand the difference between the ones that are under high pressure and low pressure, then you understand there's fewer high pressure than there is low pressure, because the low pressure ones are on the outside of the wheel, the high pressure ones on the inside of the wheel. There's less density on the inside of the wheel, so obviously there's more of the outside of your wheel than there is rubber. There's more rubber on the outside of the tire than there is rubber on the inside if it was made out of solid rubber.
Was that we assumed each standing wave mode in the blackbody had an average energy of kT. Now, clearly this seems to be true for low frequencies, but not so much for higher ones. With Boltzmann's distribution in mind, we can start to explore Max Planck's solution for this. Planck's solution relies on modelling the blackbody as an infinite collection of harmonic oscillators, tiny little masses on springs, none of which interact with each other. Planck postulates that the oscillators can only absorb or emit light in quanta of h times nu, where h is some constant and nu is the frequency of the radiation. This certainly isn't an obvious move. In fact, it's quite the opposite. When Planck first proposed it...
Right, so this is almost just giving them size. So this could almost be a scatter argument, where you would argue that you have small bits and you have big bits, and it's obvious that let's say you have radiation that's polarized and it's vibrating, moving. I mean, it's out of sequence. Well, the out of sequence stuff can't possibly affect the little bits, because one bit's going to be here, one bit's going to be here, one bit's going to be here. They can be in all kinds of places. They can't scatter off of this thing. Okay, just can't do it. But the stuff that has little variation, well, all the radiation can hit the one bit and it can scatter. So it's only possible for certain frequencies to affect certain things, because only things with that frequency have that thickness, of polarization. So their density is different in a sense. You can just make it a size argument. They're bigger or smaller based on their frequency also. And obviously, bigger is a tricky word. That's dangerous. So you could say density. They're more ghost-like. The bigger they get, the easier it is for something to go right through them. You can almost make it that argument. They're more like a screen. So when they go at something, if the thing's small enough, it goes right through the screen. So there's no event.
He and his colleagues thought of it simply as a mathematical trick. The idea that these quanta physically existed would have been ludicrous. Of course, that turned out to be the case, but we'll get to that later. With the energy spectrum of the oscillators quantized in h nu, and our blackbody being at equilibrium, we're in a valid position to apply Boltzmann's distribution and try and calculate the average energy of the system. Since we know the probability distribution of the oscillator energies, we can write down an expression for the average energy, the sum of the energies multiplied by their probabilities. If we substitute in our quantized energies...
So let's just understand. So I would argue that this is a simple argument in the sense that what they're saying is that you have initial states and you have a probability of pressure in that initial state. And now if I heat this thing, that means I'm pumping more energy in. Well, I not only pressurize more these atoms, but I also pressurize these atoms. And here too, I increase the pressure of the system. So although these proportions might stay the same, I've changed the levels in the sense that there's now a new higher pressure and there's now a new lower pressure. Something like that. And that's by some scale. And so I guess the argument would be is that it's easier to pressurize these outside of the wheel than it is to pressurize the ones on the inside. So the amount of change you'll have on the system is going to affect these electrons more than it's going to affect these electrons.
Then we get that the average energy...
It's almost the surface temperature of the Earth has nothing to do with the internal temperature of the Earth kind of thing. The internal temperature has a really hard time getting to the outside of the Earth. Just doesn't do it because it's got to move so much physical mass to radiate out through the surface. There's probably a better way to say that. I mean, obviously some of it thermodynamically is doing that, but I'm just saying it doesn't have anything to do with the temperature of the surface of the Earth. The surface temperature is being caused by the sun, not the fact that the Earth is molten on the center.
Energy is h nu over z times the sum of n e to the minus h nu over kt, where z is the sum of e to the minus n h nu over kt. A bit of a mouthful, but we can make life easier for ourselves by defining x as h nu over kt, giving a slightly simplified expression. So to calculate the average energy, we need to...
So this doesn't have anything to do with really explaining mechanism, right? I mean, this is just mathematical blah, 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 and doesn't really get to causes. What's exactly causing these relationships between things that really aren't real, right? I mean, we got a fake constant, and we got another constant down here, time, which isn't, it's important, but he's not saying anything about what's being timed and what's the rate of thermal increase. I mean, we don't even know what's being timed and in what time scale it's happening at.
Find these two infinite sums. Dealing with infinite sums itself is a massive issue, but we don't actually need to go into too much rigor here. Firstly, notice that the two sums are very similar, except that the partition function doesn't have a factor of n in front of the exponential. If we differentiate the partition function with respect to x, we get the negative of the other sum. Therefore, if we can evaluate the partition function, then it can just be differentiated with respect to x to get the other sum.
I didn't know this video was just going to be all this really obtuse mathematical gibberish instead of some real explanation about a physical drawing of a physical mechanic. I thought there'd be something in here about how an atom's structured, but there just isn't.
All we need to do then is to combine them to get the average energy. Examining the partition function, we can see that it's an infinite geometric series with common ratio e to the minus x.
Well, there's no infinite, so that's kind of horseshit.
Evaluating these kinds of infinite sums is pretty standard. It's just the first term divided by 1 minus the common ratio. This will converge fine as x is positive, so e to the minus x is less than 1. Differentiating with respect to x, we get minus e to the minus x over 1 minus e to the minus x squared. Recombining all of the terms and doing some simplifying, we see that we can cancel a factor of 1 minus e to the minus x. And doing some more simplifying, we see that we get the average energy is h nu over e to the minus h nu over kt minus 1. We can see that this fits our previous observation, that for low frequencies, the average energy is equal to kt, by using the series expansion of the exponential, and making the approximation...
So again, let's understand that the energy has nothing to do with the real term energy. It just has to do with timing. So without the t factor, all right, that's deciding the timing of how you're interacting, is deciding how much energy there is. So we're just saying, because of the circumstance, because this thing has a tipping point, it's not cannonballs that count. It's cannonballs at just the right frequency that count. And again, that's what's being lost in this whole conversation, is this word energy is getting confused with the amount of time you're timing something. It's almost like saying how smart is somebody is, based on, and then having a timed test to tell how smart they are, whether they know something or they don't know something. When the whole point would be is, can they get the right answer? Who cares how long it takes them? Do they get the right answer? That should be the objective, not figuring out how fast somebody can do it. So by throwing time in here, you're saying that energy is different if the energy is delivered in a specific amount of time. When, no, all you're saying then is that I have to put all the water in the pot in a certain speed. It's not how much water I put in the pot, it's how much I put in there in 4 seconds. But that really isn't telling you how much energy or how much water I have available, or how much water I'm putting into the system. So the point is I can put a lot of energy into a system through infrared radiation, but it's useless because the bullets are at the wrong speed. But it doesn't mean they don't have energy. It just means they can't deliver it by getting a product out. A product you're measuring. You're only measuring one thing, tipping the thing over. You're not measuring hitting it, wobbling it, heating it, doing all that crap. And so just by a rational standard, it's a density argument. Obviously, if the things are closer together, you can have more of them in a moment of time than if they're further apart. Duh.
That the frequency is small. This gives back our original statement. So now we have an expression for the average energy that captures the extra high frequency dependence that was missing from the classical Rayleigh-Jeans law. Going back to the first video, we wanted to calculate the radiance of the black body, 1 over 4c times the average energy times the density of states, 8 pi nu squared over c cubed. If we combine all of these with our new quantum expression for the average energy, we get a spectrum that actually fits the experimental data. This is the Planck law for black.
Right, and after all of this crap, you get it. So again, it seems pretty manipulative, an awful lot of work to get to the point where you're basically drawing a diagram of the how many electrons are in the outside orbit of the average atom, how much are in the inside orbit of the average atom, the average atom of the substance you're heating, and so on. And that's all that curve represents, I would argue.
Body radiation. Planck had solved the ultraviolet catastrophe using what he thought of as a weird mathematical trick. What he was really doing was glorified curve fitting, but the result was not only consistent with the ultraviolet catastrophe, but other measured phenomena too.
Yeah, well, it just points out that, look, there's a whole big pile of stuff on one side of that peak, and the peak, it just represents the peak energy. And then there's no more, you can't go any higher pressure, so there's less and less stuff coming out at that higher pressure because X-rays are even harder to make and these other things are even harder to make, and so you get even less volume of those things as part of your ingredients. So he's just saying that the very high pressure things are so few that they add up to a tiny percentage of the whole. Eventually, when you get to these very, very high numbers, it's very rare that you get this pure thing. You can even just say it's diamond purity, anything. You could just make a curve for it and say what's the average, and the average isn't necessarily a consistent average, and that's all this thing is made out of, is some argument that yes, the nature of atoms is there's a disproportionate volume in these states more, and there's very little stuff in this other state, and this is your line defining the average, but it doesn't have, the average isn't like 50-50 on either side. Well, it doesn't have to be. There's no rule that says so.
We can take our expression for the radiance and integrate over all frequencies to find the total power radiated per unit area of the black body. With a bit of manipulation, we can see that this integral is of the form x cubed over e to the x minus 1. This is the well-known Bose-Einstein integral, related to the beloved Riemann zeta function.
And again, this is stuff that isn't necessarily experimentally proven by anything. So again, this is all theoretical stuff, not really stuff that there's any hard evidence for.
But this has a closed form expression of pi to the 1 over 4 over 15. So we find that the total power radiated per unit area is proportional to the temperature of the black body to the power of 4. A quantum correction successfully recovers the well-known Stefan's law, whereas the classical model predicts that the power radiated per unit area is infinite. Now, I said that the resolution of the ultraviolet catastrophe gave rise to quantum mechanics, but in some way that's a lie. Planck's solution remained pretty much untouched for about 5 years, until another radiation-related problem came along, solved by a young Einstein, suggesting that Planck's mathematical quanta were in fact real physical particles.
Yeah, duh. And those are the particles, the bits that make up the very thing you're talking about having a frequency, which is the irony. So they figure out this quantum thing. But again, Einstein's perception, that his evidence that it comes in clumps, isn't very good evidence because he's still measuring what we can detect. We can only detect clumps. So that's the whole point. We still don't have a way of detecting something that wouldn't have been a clump, right? So the point is if it's there, we can't detect it anyway. So you can't make a declaration that the double quanta doesn't exist because you don't have any way to detect it if it did. And so that's kind of the imbecility of the conclusion, is that it's not very good evidence that it comes in clumps when your way of detecting requires it to be in clumps. The whole point is something like a photodetector or anything that's going to detect these things, even something detecting an electron, is dependent, okay, on it showing up in a certain condition. And if it doesn't show up in that condition, you can't see it. Anyway, just as I've sort of pointed out with photons, you could break one. You could take one bit out of the one quanta out of the photon's still 99% there. You can't see it. I can just screw up its polarization a little bit. You can't see it. Still the same thing fundamentally. Still all the same energy is in it. But we can't tell it's there. And that's sort of important. I mean, there's a real detecting problem. And drawing too hard a conclusion on too scant evidence. So again, just as I would argue, there are experiments to detect the volume inside of an atom, how much of it is stuff and how much of it is empty space. It's kind of a thin experiment to draw such a hard conclusion. So anyway, I think that's probably enough for today's adventure. Like I said, I'm sort of liking the idea of the reflection, light reflecting off of protons. In the case of a reflection, that the reflected light is more likely to be light that reflected off of a proton. Not that it couldn't be from an electron, but the likelihood of the electron would be changing its color or causing some other effect, where the proton would leave the original photon pretty much intact, theoretically, which is interesting. We'll think some more and such. Let me just see if there's any new comments, which isn't very likely. Nope. So, till the next video and such. Let me see if there's anything. The subscriptions are just horrible. These videos are just... Look at the electric universe. It's talking about how special Venus is. Long-haired star, great comet. So, I mean, people say it's not a religion, and it's just full of all this crap, of trying to turn it into something mystical. And the fact that people 1,000 years ago didn't have a brilliant conception of what the hell was up in the sky. Just amazing. But somehow we should take their guesses seriously. Somehow they made better guesses than we could make. No, I don't think so. I don't think so by a long shot. Fuck. Hair. Yes, there's hair on Venus. Electrical hair. Whatever. People be stupid. That's all you can say. No, there's a lot more.